Hi, and welcome to this. It's a bit of a go through on a lesson on relative atomic mass and looking at percentage composition. So if we look at this, we're going to use our periodic table, so make sure you have one handy with you. It's really almost impossible to actually compare physical chemicals because there's so much different between the atomic structures in them that it makes it very, very hard to work out what's going on. And then of course we've got those wonderful things called variations in the atoms called isotopes that makes it even more hard. So it's one of these things. So what scientists have done in an effort to make it a bit easier is we've compared the average atomic mass against various elements or various isotopes. And these days we use the carbon-12 isotope as our standard, and we have our relative atomic mass compared to that. So we're talking about, in the case of these ones here, we're talking about the case of the relatively atomic mass of manganese in this case is this, and that is compared to carbon-12 isotope. And then if we go to its next door neighbour on the periodic table, iron, we find that that is the comparative mass or relative atomic mass. Okay, so that's the number that you have to look at and we use a lot in calculations. So what we actually use to make it the only comparative tool that it works really well in chemistry is using a thing called the mole. And it uses the relative atomic mass of the atoms or the elements and their natural state to work out what's going on. So for any element, 1 mole is equivalent to the grams of substance expressed in relative atomic mass on the periodic table. But we must consider the natural form. So you must find out whether it's a monatomic, whether it's diatomic, or how it forms together. And this is a bit of a problem if you struggle with formula. But you must push through with it, and it's the easiest way to do it. Don't forget that certain things exist as diatomics, and we must take that into consideration when we're working out what 1 mole is. So if we look at the one with the obvious one here, we've got oxygen gas. Now oxygen gas is obviously O2, we know that. It's the stuff we breathe. So it's O2, in other words 2 atoms of oxygen. So we have to look at the 1 mole of oxygen gas is 2 times the RAM, or 2 times 16.00 from my table sitting in front of me. So it's going to be 32. Now, since we're talking about rams, or we're talking about moles, 1 mole would be 32 grams of oxygen. That would be 1 mole of oxygen gas. If we were talking about just the atoms, we're talking about atomic mass units, so it would be 32 ATMs, AMUs, atomic mass units. All right. Now, if we consider these other ones, I've done the same sort of thing with the allotrope of oxygen called ozone, O3. In this case, I've got 3 atoms of oxygen per molecule, so it becomes 3 times the RAM, so 3 times 16, so that gives us 48 grams, corresponds to 1 mole of ozone. Right, so let's consider what's going on with the compound. If we do a compound, the same sort of thing applies, except we've got to add the RAMs of each of the atoms involved, or each of the elements involved. So let's look at this first example, copper 2 oxide. So copper 2 oxide we must put down as formula. Copper, it's got a combining power of 2 or a valency of 2, it tells us that here. Oxygen's got a combining power valency of 2, so copper 2 oxide is that. So therefore 1 mole is going to be equal copper, and if I go to my periodic table, copper it says 63.55, and I've only got one of them, so we leave it as one. I've got one oxygen, which is 16, so if I add those together, I end up with 79.55 grams per mole. Alright? Now this is the tricky part for some people. Some people find this part tricky, converting that to that. Hopefully your formulas are going to be good, and hopefully you are going to understand what is going on. Let's do one more example. Now we've worked out how much is in 1 mole, we can work from there. So we've got, over here we decided 1 mole of copper oxide, which is going to be 79.55 grams. So the question now asks us over here, what percentage of this is due to oxygen? Alright, so we know that the percentage due to O is equal to what mass, or the RAM of oxygen, which is 16.00, over 79.55, the total mass of my substance, right? So this is due to oxygen times 100. So we can see this mass is due to oxygen. This is my total mass, so we're after the percentage of the total mass. So there's my total mass of copper oxide. There's my mass of oxygens. So when I actually go through with that, I see that that is going to be very close to 20%. Alright, now you should do a calculation, of course. You don't just write down an approximation. But I know 79.55 is almost 80, and there are 5 16s in 80. So that means I've got 1/5 times 100, which is 20%. Now, this follows the same rules apply to every calculation you need to do. Every calculation. So no matter what the chemical is, you start off by writing its formula. Make sure it's correct. Then you can work out how much 1 mole is. Then from your periodic table, you can work out the ratio of each of the elements, how much it is. If it's got 10 different elements in it, it doesn't matter. The same rules apply. Now the interesting part is, if 20% is due to oxygen, that means 80% of the mass of the compound is due to copper. And that's all we have to do. The only problems you're going to struggle to find in your test and exam questions are going to be a bit more complex than this. But the same rules apply. And on that note, I'm going to let you practice.